we're not going to be designing a reinforced concrete column in this lesson. So if you take a look at the screen, we want to design a square tie column to support an axial dead load of 130 kip and an axial life load of 180 kip. So FC prime is 4 KSI, so this is the compressive strength of the concrete, while Fy, which is the tensile strength of the steel, is 60 KSI. And we are going to begin our design using 2% longitudinal steel. So if you remember in the previous video, I said when we want to start our design, we usually start from 2% to 8%. And the longitudinal steel, that is a 2% longitudinal steel, this is going to be the reinforcement ratio. That is how much steel we have in the column and how much concrete we have in the column. So basically we are going to say 2% of the column comprised of steel. So this is just as an assumed value. So we can correct this later on when we designing the column. So let's start. So we are going to take a look at the first step. So the first step is you need to calculate the factor load PU. So this is the first step we are going to take. So let me write this here. So step 1 is we need to calculate the factor load PU. So if you remember in the previous video, I said PU is equals to 1.2 multiplied by the dead load, then plus 1.6, then multiplied by the life load. So all we need to do, we just need to input our values so that we can calculate for PU. So this is going to be equal to, so PU is equals to 1.2. So what is the dead load? The dead load, as you can see here, is 130 kip. So this is going to be 1.2, then multiplied by 130 kip, then plus 1.6, then multiplied by the life load. So we have an axial life load of 180 kip. So this is going to be multiplied by 180 kip. So all you need to do, you just need to use your calculator to calculate this value. So if you use your calculator, you are going to get the factor load PU is equals to 444 kip. So this is the factor load PU, 444 kip. So now we know the factor load. The next step we are going to take is we are going to assume the reinforcement ratio, and we already assumed the reinforcement ratio, and we said the reinforcement ratio, this is basically 2% longitudinal steel. So let me just write this down here so that you can easily follow this. So this is step 2. Step 2 is we usually assume the reinforcement ratio. So in this case, we assume the reinforcement ratio to be 2%. So we're having 2% reinforcement ratio, 2% reinforcement ratio. So this is basically rho G. So rho G is equals to, so if this is 2%, then all you need to do, you just need to divide this by 100. So you are going to get rho G, which is 0.02. So 2 divided by 100, you are going to get 0.02. So this is the reinforcement ratio. So you can also get the amount of concrete we have in a column. So you just need to subtract 0.02 from 1. So 1 minus 0.02. So this is going to give us 0.98. So what this means is the amount of steel we have in the column is 2%, while the amount of concrete we have in the column is 98%. Now the third step is we need to calculate the gross area. So that is the minimum gross area. We need to calculate the minimum gross area. So this is step 3. So you just need to follow this step by step. If you follow this step by step, you're not going to have any problem designing a reinforced concrete column. So if you remember in the previous video, we saw the formula for the minimum gross area, which is AG minimum. So AG minimum is equals to PU, which is the factor load, then divided by phi, then multiplied by alpha, then multiply by 0.85, then multiply FC prime, then open brackets 1 minus rho G, then close the bracket, then plus Fy, which is the tensile and strength of the steel, then multiply by rho G, then you close the bracket, then all this is inside one parenthesis. So you just need to extend this side. So now this is the formula for AG minimum. So all you need to do, you just need to input your values to calculate for AG minimum. So let's input the values. So this is equals to, what is PU? We already calculated PU. PU is 444 kip. So input this here. So we're having 444 kip, then divided by. So what is phi? In the previous video we said that phi is going to be 0.65 if we are dealing with a square column. That is, if we are dealing with a tie column, which can be square column or which can also be rectangular column. So phi is going to be 0.65. But if it's for spiral column, the value is going to change. But because in this case we are dealing with a tie column, that is a square tie column, the value of phi is going to be 0.65. So this is 0.65. Then multiply by, what is alpha? Alpha is 0.80. If you remember in the previous video, we said alpha is 0.80 for tie column. So this is going to be 0.65, then multiply by 0.80, then open bracket, then 0.85, then multiply FC prime. So what is FC prime? FC prime, as you can see over here, is 4 KSI. So this is 4 KSI. So which is 4 kip per square inch, 4 KSI. Then multiply. So when you need to open your bracket, then multiply by 1 minus rho g. So we already calculated the 1 minus rho g, which is this value. So as you can see, 1 minus rho g is going to be 0.98. So you just need to multiply this by 0.98. So this is multiplied by 0.98. Then, so now we have plus Fy. Fy is the tensile strength of the steel, and this is 60 KSI. So this is plus 60 KSI. Then multiply by the last value, multiply by rho g. So rho g is 0.02. So this is multiplied by 0.02. Then you need to close the brackets. Close the bracket. Then you just need to calculate these values using your calculator. So if you calculate this value using your calculator, you are going to get AG minimum, which is the gross minimum area. AG minimum is going to be equals to 188.4 inch square. So this is the minimum gross area. So that is for step 3. So now we need to move to step 4. So what are we going to do in step 4? In step 4, we are now going to select the column dimension. So this is going to be for step 4. So this is step 4. We are going to select, for step 4, we are going to select the column dimension. Now, we know that this is a square column, so meaning the width and the depth are going to be similar. So we are going to have the same value for the width, and we're also going to have the same value for the depth. So in this case, meaning this is just going to be the square root of the gross minimum area, because the sizes are similar. So B is going to be equal to D. So it is just going to be the square root of the gross minimum area. So it is going to be B, which is the width and which is also the depth. It's just going to be equals to the square root of AG minimum. So B is equals to the square root of AG minimum. So this is B is equals to, what is AG minimum? We calculated AG minimum as 188.4 inch square. So if you take this, that is the square root of 188.4, you are going to get 13.73 inch. So this is going to be the value of B. So if we have B as 13.73 inch, then D is also 13.73 inch because it's a square column. Now, this is where you need to pay close attention. We have 13.73 inch. Are we going to just take this value? Are we going to just take 13.73 inch as the width of the beam? I don't think so. No engineer is going to design a beam width of 13.73 inch because it is not going to be easy for the workers to input the steel in the beam. So it's going to be very confusing. So what you need to do, you need to try to make your column width to be in even pattern. That is 2, 4, 6, 8, 10, 12, 14, 16, 18. So try to make it even. So if, for example, if you have, let's say 12 points, if you have, let's say 13.5, just round it up to 14 inch. If you have, let's say 15.3 or 15.1, then just round it up to 16 inch. So always try to make the size of the column, try to make it even. So now, because we're having 13.73 inch, we are just going to round this up. We're going to round this up to 14 inch. So now this look better. Instead of 13.73 inch, we now have 14 inch. So this look better. So meaning the sizes of the column is going to be 14 inch by 14 inch, because this is a square column. So now we know the size of the column. We need to change our gross minimum area. So we are going to have a new gross minimum area. So we are going to use the new size of the column, which is 14 inch by 14 inch. So basically 14 multiplied 14 is going to give us 196 inch square. So this is going to be the new gross minimum area. So instead of 188.4 inch square, we are now going to have 196 inch square, because we now know the size of the column. So it is going to be AG minimum is going to be equal to 196 inch square. So this is our new gross minimum area. So now we know this, we are going to move to the next step. So on the next step, we are going to calculate the minimum area of steel. So this is for step 5. So step 5, we are going to calculate the minimum steel area. So in the previous video, I already showed you guys the formula. So if you want to check the formula, just go back to the previous video, then you get the formula. So AS and T minimum, this is equals to PU, then minus phi, then multiply alpha, then multiply 0.85, then multiply FC prime, then multiply AG, then divided by phi, then multiply alpha, then multiply Fy minus 0.85, then multiply FC prime. So this is the formula for AST minimum. So all you need to do, you just need to input your values. So what is PU? PU is 444 kip, then minus phi. Phi is 0.65 minus 0.65, then multiply by alpha, and alpha is 0.85. So this is multiplied by 0.85, then multiply by 0.85, then multiply by FC prime, which is 4 ksi, 4 kip per square inch, so 4 ksi, then multiply by AG. Now the AG is going to be your new gross area. So the new AG is going to be 196 inch square. So don't make the mistake of taking the previous AG. So be careful with that. So this is going to be divided by phi. So phi is 0.65, then multiply by, so this is multiplied by alpha, and alpha is 0.80, then multiply by Fy, and Fy is 60 ksi, so multiply by 60 ksi, then 60 ksi, then minus 0.85, then multiply by FC prime, which is 4 ksi. So multiply by 4 ksi. So all you need to do, you just need to use your calculator to calculate this value. So let me take this down. So all you need to do, you just need to use your calculator to calculate the value. So if you use your calculator, you are going to get AST minimum, which is the minimum ST area, is equal to 3.312 inch square. So this is the minimum ST area. It is 3.312 inch square. So now we know the minimum ST area. So what we need to do is, using the minimum ST area, we are going to select a reinforcement pattern. So this is the next step. So this is step 6. So step 6, we are going to select, so let me write it here, select a reinforcement pattern. So we are going to be using the beam design and aid table, the beam design and aid chart to select a good reinforcement pattern for our column using the area of steel as 3.312 inch square. So I'm going to show you the beam design and chart. You can use the beam design chart to select a reinforcement pattern for our column. So as you can see on the screen, we have the reinforced concrete beam design aid. So as you can see, this is the table we are going to be using to select a reinforcement pattern. And we said the area of steel is 3.31 inch square. So how can we select the reinforcement pattern? So what you're going to do is, as you can see on the column side, we have the number of bars, while on the row we have the bar size designation. So on the number of bars is basically how many steel bar is going to be in the column, while the bar size and designation, so this is basically the size. So this is basically the size of each steel bar. So don't confuse this. So what we're going to do is, since we have the area of steel as 3.31, so let's approximate this to 3.31. So since we have it as 3.31, you are going to take a look at the closest value to 3.31. So let's take a look at this. The closest value to 3.31 here is the closest value. So you need to try to be as close as possible. So the closest value to 3.31, and make sure the value need to be greater than 3.31, because we said this is the required area of steel. So this is what is required. So we can't go below this value. So it needs to be above this value, but not too far away from this value. So we need to try to make it as close as possible to 3.31 without going below 3.31. So this is our goal. So let's try to find a good value here. So I think we are going to have 3. Let's see. So I think 3.53 is okay. As you can see, 3.53 is greater than 3.31, and this is the closest value to 3.31. So if you take a look at this, we have 3.53. So now what I'm going to do on the column side of 3.53, the number of bars is 8. So we have an 8 number of bars, while on the row side, the bar designated size is number 6. So meaning we are going to be using 8 number 6 bars. So meaning we have an 8 steel bar inside in the column, and each bar side is number 6. So this is what it means. So we said we are going to be using. So we'll say use 8 number 6 bars, and we use this because the area of steel was 3.53 inch square. So this is what we are going to be using. So this is the reinforcement pattern. We are going to be using 8 number of bars, and each bar is going to be number 6. So take note of that. So now this is step 6. Now for step 7, we need to select transverse reinforcements. So step 7, we are now going to select the transverse reinforcement. So basically, transverse reinforcement, these are basically the stirrups. So now we are going to select this based on 2 parameters. So we are going to be taking a look at the size of the ties, and we're also going to be taking a look at the spacing from one ties to another ties. So these are the 2 values we need to get. So let me write this down here. So we need to get the tie size, and we also need to get the tie spacing. So we need to get the tie spacing. So for the tie size, what did we say concerning the tie size? If you remember in the previous video when we discussed the step for designing the reinforced concrete column, we said when we want to choose the tie size, we are going to choose number 3 bar if the longitudinal bar are number 10 or smaller. But if the longitudinal bar are greater than number 10, we are going to be using number 4. So take note of that. So if we have the longitudinal bar as number 10 or smaller, we're going to be using number 3 bars. But if they are greater than number 10 bars, we're going to be using number 4 bars. So as you can see, we are using number 6 bars, and number 6 bars is obviously lesser than number 10 bars. So meaning we are going to be using the tie size as number 3. So we are using number 3 tie size because we're using number 3 tie size because we're having a longitudinal. So let me write this down here. So we're having a longitudinal bar as number 10 or smaller. So that is why we are using number 3 bars. If the bars are greater than number 10, then we are going to be using number 4. So take note of that. So for the tie spacing, we are going to be taking a look at 3 values. So the maximum of these 3 values is going to be the tie spacing. So what values are we taking a look at? We are taking a look at the 48 tie, that is 48 multiplied by the tie bar diameter. Then we're also taking a look at 16 then multiplied by the longitudinal bar diameter. And lastly, we are going to be taking a look at the least lateral column dimension. The least lateral column dimension. So the maximum between these 3 values is going to be the tie spacing. So let's take a look at the first one. 48 multiplied by the tie bar diameter. So what is the diameter of the tie? As you can see, is number 3. So because it is number 3, meaning you need to divide this by 8. If the tie size is greater than number 8, then all you need to do, you just need to take a look at the diameter of the bar. But if it is lesser than number 8, then all you need to do, you need to take the bar size and divide it by 8. Hope you get that. So now because number 3 is obviously lesser than number 8, then we are going to divide 3 by 8. So it's going to be 48, then multiply by 3 over 8. So if you calculate this, we are going to get 18 inch. Then 16 longitudinal bar diameter. So this is going to be equal to 16, then multiply. So the longitudinal bar diameter. So the longitudinal bar diameter, as you can see here, is number 6. So because this is also lesser than number 8, we are going to divide the bar size by 8. So hope you get that. But if it is greater than 8, then you just need to take a look at the diameter of the bar. So this is going to be multiplied by 6 over 8. So if we calculate this, we are going to get the value as 12 inch. Then the least lateral column dimension. So basically, this is just going to be the column dimension because we are dealing with a square column. So the size of the column is basically 14 inch. 14 inch. So the maximum between these 2 values is going to be 18 inch. As you can see, 18 inches is greater than other values. So we are going to be using 18 inch. Now, the reason we are taking a look at the maximum values between these 2 values is between the 3 values is because for the ties we want less spacing as possible, because with less spacing mean the cost of the steel is going to reduce because we are going to have less ties on the column. So we are trying to use the least tie spacing as possible, but make sure you do not compromise the safety of the column. We are trying to use the least tie spacing as possible, but we also need to make sure that the spacing we choose is efficient. So we have the tie spacing as 18 inch. So this is 18 inch. So now we know the area of steel, we know the tie size, we also know the tie spacing, and we also know the width of the column. So we are basically done. But this is not the end, because everything we calculated so far was just basically an assumed values. So we need to check if our values is going to be okay or not. That is, if they meet ACI requirements. So we need to make the check. So we already have the width of the column. We already have the area of the steel. We already have the reinforcement pattern. We are using 8 number 6 bars. We already have the tie size. We already have the tie spacing. So all you need to do, you just need to check if everything you solved so far is correct,